Okay, so let's start. So we have a new chapter today, mainly concerned with like unitary and uh, basically like non-continuous evolution in quantum mechanics. Maybe later a bit of geometry and spin, but today we will talk mostly about like U and R processes, some their uh, properties, and like unitary evolution and maybe Heisenberg picture. I didn't manage to write a summary for Heisenberg, but I'm still able to talk about that. Yeah, so anyway, let's start with first subchapter. So yeah, and we will have like much faster pace today because uh, I'm kind of getting out of the illness, and I probably won't be able to talk much today. So I think we will go through it faster than usually. Yeah, so in the first subchapter, Penrose basically just like makes an overview of the previous chapter, and he talks that it is hard to depict quantum mechanics, but he is uh, kind of voting for digging for some visual intuition there, and he says that we've seen that we can use a wave function for a single particle depiction, and and we can think that that's enough, but in the case of the many particle system, we will see that instead of having n separate state vectors, that system will have just one, which is kind of entangled in some way, and we will learn about entanglement more in chapter 23. Yeah, and even for one particle, we still will need to understand, for example, what a spin is to make a nice quantum mechanic or like geometrical picture for quantum system. Yeah, and on the next page, he just says that, like in the previous chapter, we've seen that state vectors, um, like we have the state vectors and we have their evolution described with Schrodinger equation, and also jumps while measuring something, and we can talk about those or depict that as like localization and spreading of the wave packets in different bases like P or X. And as we'll see, a measurement could be described using some Hermitian operator, Q, for example, and during the measurement, a state jumps to its eigenstate, and apparatus shows us the eigenvalue as a result of the measurement. And that process could be called R, which kind of stands for the state vector reduction or wave function collapse. And most physicists think about the R that the R is not the real action of the physical world, which reflects um, which reflects that state vector is not real in some sense, and there will be more information about that in chapter 29. All we know is that Schrodinger evolution, uh, depicted here or called here just with U letter, is intertwined somehow with the R evolution, and it's actually depicted on the figure 22.1, that we have like continuous U evolution and then just jump when we do some measurements there. So we kind of have like a chainsaw pattern over the time. Yeah, and that is actually like the odd way for the universe to behave, and we can think that this scheme is just an approximation of something to be discovered, but nowadays like most physicists doesn't believe in that, firstly because we have precise predictions of the current theory, and secondly because they often use some kind of philosophical standpoint which relieves the tangent between those two. uh, we'll talk more about the problems and like the ways to new discoveries in chapters 29 and 30. But to start talking about those deep matters, we need to understand conventional quantum mechanics nicely. And inside the conventional view, R is just a convenience, giving us the best predictive results in our experiments. Yeah, and we will also learn more about unitarity of Schrodinger evolution and other equivalent way to describe it, Heisenberg's picture. So basically that's it for the first subchapter, and personally for me it's kind of the overview of the current chapter, and I think the most interesting part here is about like that relationship between U and R, and maybe like the idea that maybe some kind of the new theory could be built and some new like revolution made in quantum mechanics on the connection of U and R processes. Any questions about this? Okay, so let's go for the next one. And the second subchapter here talks about the linearity of U process and its problems for the R. So we can take the Schrodinger equation, and from the just the general form of it, we can get some immediate consequences. Firstly, it is deterministic, so evolution is fixed starting from some known point. So we have kind of the differential equation, and by fixing some initial condition, we can just predict continuously how the system will evolve. The same is in like Newtonian mechanics. And secondly, it has complex nature because we have imaginary I in it. And finally, it's linear because if we have like psi and phi, which are solutions, then also their linear combination will also be a solution. But like Schrodinger equation is about like local solutions or like infinitesimal things, and therefore on the next page Penrose talks about that basically Schrodinger evolution preserves vector space structure of the wave function space, and Hamiltonian defines infinitesimal linear transformation of our vector space W that describes the change in the state over infinitesimal time. So basically it's just a vector field on wave function space. And to obtain the finite linear transformation instead of some kind of infinitesimal one, we need to exponentiate that and obtain some linear transformation t for a finite time for the changes in the state. And it's kind of similar with what we've seen with in Lie algebra and Lie group theory in chapter 14. So yeah, but in this case the nature of it will be a bit difficult because of infinite dimensions, but anyway it doesn't matter for now. The point here is that the finite change for our wave states or wave function will be described with the some linear operator t defined on the space W, and that's like the main point here. Yeah, and on the next page Penrose starts to talk more about like philosophical viewpoint, like after we finish with math, that basically if U is the whole story and R is just some kind of convenience or approximation, then we can get some paradoxes. For example, we can recall the 21.7 example from the previous chapter, in which we have had like two researchers, right, and the like one photon kind of how to say it, like split it in two wave functions, right, like wave packets traveling over space, and we have had like two detectors for like two researchers. And basically what it tells us that like after splitting, the wave function is described like a sum of two wave functions, and the Schrodinger evolution tells us that like both detectors should kind of react and give us some results. But actually that's not the case. And what we see in reality is just like one of those will respond, and that happens during the R, like the wave function collapse. And the only way to think that the whole story is to use many worlds view or theory, but even then we can't explain what are those worlds basically and how our consciousness breaks reality down and why we are not able to perceive superpositions of wave functions. So Penrose just points out that many worlds view is by his personal opinion is just a result of believing in you only. Uh, yeah, so it's kind of giving up on explaining the interconnectedness between U and R and what R actually means. So he finishes this subchapter with the paragraph kind of motivating us just to stick for conventional quantum mechanics as for now and wait for the next chapters 29 and 30 to discuss more about the philosophy and like deep insights of the quantum mechanics theory. Any questions about this chapter?
There's a lot here, and I wonder if we can try to kind of like explore some of the philosophy around it, just because it's really interesting that like in order to get the R process as it's used in standard quantum mechanics, usually we consider that like the detector or the measurement device, whatever it is a classical system. And that's what ends up collapsing the wave function, is that we get a particular value measured. But it seems to lend itself to this many worlds idea if you consider the detector as a quantum object as well, so that the outcomes, like rather than measuring a single value, there's a probability of measuring any particular value, and that probability could be zero or very small. But if you envision the detector as a quantum system, it really lends itself to this idea that U is the whole story.
Yeah, and actually I think I've seen some video probably on Veritasium channel about many worlds, and he he used there the Schrodinger cat example, like when the classical big like macroscopic system could become like a quantum mechanical one in terms of like the unstable nuclei in a box and some radioactivity detector inside, right?
Right, and it just seems like R is the way that we perceive the world, but if you consider these things as like macroscopic quantum systems, then it would still be a U-type evolution.
Yeah, it's interesting. It's interesting, and actually in that video, probably Sean Carroll was, and he has a book about the many worlds theory, and I think he kind of how to say votes for it basically.
Could you explain a little bit more so I don't quite understand the mm, by 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 eliminating this R process, do you mean that uh, there is no collapsing process?
Yeah. Like there is no collapse. Actually, the world splits. So we have like two alternative worlds. So in example of the Schrodinger cat, right, where we have like some radioactive thing in a box and a cat inside, and with some probability that atom will kind of kill the cat because when radioactivity detector will detect some how to say that like radiation, right? It will just crack some cyanide gas or something, and the cat will die. So we have like a quantum mechanical probabilistic model in a box, but you do not know is cat dead or alive inside the box, right? So basically, it's kind of the superposition of two states, two variants, like uh, the nuclei radiated something and cat is dead, or it will not radiate. And basically, you are kind of entangled with that system, and when you open the box, you could have like two alternative worlds, two alternative results for like to be collapsed to. But if we think that collapse doesn't happen, it's just that both worlds exist at the same time. Like there is a version of me seeing the cat dead, and there is a version of me seeing the cat alive simultaneously, something like that.
Seems that it's just the collapsing process becomes the process where these two states unentangled, because then how is the process that before you the states simultaneously exist, and then after the states becomes separate where one doesn't perceive the other state?
Well, that's exactly the idea of like picking your detector to be classical. That's the only thing that enforces that we get like one particular outcome from a measurement. But if you choose that the detector is a quantum system, then it evolves with this U-type evolution as well. And so as the cat is in superposition, you interacting with the cat puts you in a superposition, the same one that the cat was in.
Yes, so basically we kind of sucked up into big one wave function state of the world, right?
Yeah, well, and it's not even just like the world. It's more than the world. Like if you this gets more into
Yeah, so
semantics.
it's kind of the superposition of alternative worlds.
Yeah, so there's four total possibilities, right? There's the cat is dead and you see it dead. The cat is alive and you see it alive. The cat is dead and you see it alive, or the cat is alive and you see it dead. Two of those are not sensible. But the thing is, if it were truly a U-type evolution, then there would be like four total worlds where those are the outcomes.
It's interesting, like in the context that like we are kind of hallucinating our reality, you know. And I've thought that like probably sometimes I can like with a really small probability I could see the alive cat while it's dead.
Yeah, that's exactly like the real weirdness of it is like the cat could be dead and you observe it to be alive. And that's just like one of the branches along this many worlds. But the R process is really just picking one of those outcomes. Like it's not like we have four actual outcomes. If we say I am a classical system and when I observe the cat, it collapses the wave function. What you have to do is pick one of those outcomes. So it really just, the R process comes in from assuming that you're a classical system that's detecting a quantum system.
So am I getting this correctly that without this R process, then the state would still be entangled?
Yeah, that's right. So initially the cat is in an entangled state of dead and alive. And then after measuring, if like your measurement device is a quantum system, then it's an entangled state of four different outcomes, the ones that I listed before.
Okay.
Yeah, so it seems everything entangles up and up and up and up.
Yeah, and this, I think Penrose mentioned it as like the U process is like a spreading out. And so I think that's what this means. Like it just continually branches into more and more and more different states to be entangled.
Yeah, but I think that by saying spreading up, Penrose meant something else, like that our probability distribution just changes and like particle became more and more um, like buttered up over the space, and that's it. But we we were not yet talking about entanglement, right? So probably like when he been talking about the spreading of the wave function, I think that he wasn't talking about those entanglements, and he
I
just meant the change in the probability, and that's it.
I agree. I think that we're all understanding each other here, although I think that we're using entanglement incorrectly. Like
Maybe, yeah.
I think when we say entanglement, we mean it's superposition.
Right.
No, I'm not saying that probably, like, not, huh.
Well, so there would be.
I'm just thinking about states, right? So, for example, if I have some kind of the, well, for some reason my, oh, okay, so Chrome is here. I just been talking about states, and like for the cat we have like cat, for example, and atom state, and like cat alive and atom like radiated, right? And that's what I mean by entanglement. Like new object appears inside state,
Uh,
inside wave function, and like if we have humans and human C and the cat, blah blah blah. So it's like three dimensional vector in new space, more dimensions here basically. So that's what I mean by entanglement, not superposition. And superposition is just like superposition of all possible variants inside that more richer space of wave functions.
I think that's right, because there's the superposition of the states of each individual system, and there's entanglement between the systems. So it's like the atom is in a superposition of decay and not decay. The cat is in a superposition of live and dead, and the human is in the position of seeing or not seeing. And all three of those systems are entangled. I see what you mean.
Yeah, so something like that. But yeah, we can have all of those other variants also added at the end of that big expression, and amplitudes also. So it's just like schematic.
So are you saying superposition and entanglement are basically the same things, waves overlapping but on different scales? Well, one internal and others in well,
Yeah,
relationships, a system.
I think you will understand it better in chapter 23, because like the trick with the entanglement is actually that if you have like one system, for example, like wave function A and some kind of wave function B, right? Then you can think that you can make something like that, like using those two one dimensional basically wave function. You can construct a B function in the two-dimensional space like V squared. But actually it's not true for the general states in V squared space. So if you tensor like that X here is like tensor product. So if you have some kind of the AB wave function in a more richer V squared space, there like space of the entangled systems of A and B, there are some states which cannot be described as the tensor product of simple states in the one-dimensional system, like A and B. So that's like the power of the quantum computation. It comes from here, because like space of the entangled systems is much richer than the Cartesian product of the one-dimensional wave function spaces.
Right, so we get new properties when they're in a system.
Yeah. So it's much richer and more powerful in terms of computation, for example. And therefore, like superposition is just like summing up different basis vectors, different variants in the space, in the vector space. But we are when we are talking about entanglement, we are talking about the like moving from the more poorer wave function spaces to more richer ones, like AB here. And those richer spaces, they will have some non-trivial states which could not be described in terms of the previous systems. So basically, it's kind of means that A plus B system or like AB system is greater than A multiplied by B or something. So entanglement give us like more powerful systems.
So would you say it's a superset in that entanglement can have just the properties of superpositions, but also others?
This space of the entangled systems A and B will include the basic states for the unentangled systems A and B, but it will include also entangled states, and those entangled states could not be described in terms of A and B systems separately. So you cannot separate A and B from, in those states. They are kind of the one scene. And probably.
And there are no special cases for this where you could describe an entangled system as a superposition only. You're saying that there's always some additional complexity.
Yeah.
It's a little technical question, maybe.
Yeah, but anyway, we need to handle spin before. So after we will handle a spin and understand more about spins, we will go for the entanglement, I think, and we'll see more of those like superpositions, some vectors, and etc. So I think we just do not need to run.
Yeah,
ahead.
This is fine now. It was very interesting.
Okay, so probably we should continue just to be on time. Yeah, and actually the next two sections will be much shorter. So in the next one we will talk about unitarity in just like theoretical setting. So basically unitarity is just about the norm preservation for our wave function, and from previous chapter we can remember that the norm is defined as the integral over the whole space of the squared modulus of our wave function. Yeah, and norm is actually important for both U and R, and we can think about that as a kind of square length of the our state or function or vector. So we should be and that thing, the norm, should be finite for appropriate physical realizable states. We can also think of it in a more specific case as a Hermitian product, stated here like psi here. So Penrose marked that as the norm, but in mathematics usually we take a square root of that, so we will obtain not a square length but length. But like from theoretical perspective, it doesn't really matter. Like you're just redefining the values, right? And the normalizable wave functions, they constitute a complex vector subspace H of W, which is also a Hilbert space, and Hilbert space is just a space having the scalar product. In that case, because it's complex one, it's called Hermitian scalar product. And you can observe on page 534 some properties for that scalar product, like linearity in both arguments and antisymmetry with like complex conjugation there, and also positivity for the psi scalar product. Okay, and that psi scalar product would be equal to 0 only in case that psi is 0 wave function. Yeah, and at the end of that section, Penrose talks tells us that the notation used here is called Dirac notation, and we can call the vectors described like these as a cat, and vectors with the arrows going into the other direction is they are called brass, and basically those are the elements of the dual space H star, and basically that's just the space of linear functionals on H, on our Hilbert space H. So therefore, combined together, they will give us a scalar product, because linear functional on a space taking some vector of the H will just give some constant, in that case complex one. So we will obtain the Hermitian product using those, the same way one forms were applied to the vector fields, for example. And we can also sandwich the linear operators inside those, like these. In this case, we can think of L kind of acting on the right one, but so basically if L acts on the right one, on the cat, to find the dual thing for the bra, we need to take bra and act on it using the adjoint operator L star. So basically, if you think about the like applying linear operator on bra, you need to think about taking the adjoint there, and yeah, no adjoint for the Hilbert space for the cat. Yeah. Any questions about this chapter, about theory? Maybe you have some. Yeah, give me a sec, I need to pour some tea.
I guess just a shout out for Dirac's imaginative notation.
What?
I think it's pretty funny. I think it's pretty funny, his notation, that they call it bracket.
Yeah, it's kind of pun there, yeah. And in the next subchapter, we go straight forward to kind of proof of the unitary evolution, and now we can talk about unitarity in terms of scalar product preservation now, and Hamiltonian should keep us inside Hilbert space H and be Hermitian, and Hermicity here give us the real eigenvalues, basically real values to be measured for, and also we can require it to be positive definite. So basically, if you sandwich it inside that thing and place H here instead, that thing should be greater than 0, and such an operator will have only positive eigenvalues, which means that we will obtain only positive real numbers for the energy levels, but we do not need this for proving the unitarity. So, and on page 536, you can see the equation. Equation like taking the d by dt of the scalar product of two wave functions like psi and phi, and by using Leibniz rule and kind of using the Hermicity of H operator, we can just kind of subtract like those two parts and obtain 0 at the end. So basically we can prove that the scalar product of two wave functions using some infinitesimal evolution, they will not change. Yeah, so basically those will be preserved. And now we can think about those in terms of like more general finite time evolution. So if you have, yes, that will mean that we can describe the evolution described by Schrodinger equation using some unitary operator in finite terms. And all scalar products of wave functions are preserved over time. So basically, Schrodinger equation will preserve those. Yeah, and there is interesting fact here that the same argument applies to the generators of special rotations and translations, showing that these also correspond to unitarity transformation of our Hilbert space. And I think that's exactly what we have seen on the previous call when Joe were doing his presentation, right, Joe?
Yeah, so we did it for translations with the momentum operator.
Yeah, and we kind of proved that infinitesimally is Hermitian, and therefore for finite things, after exponentiating it will be unitary. Yeah, so basically that's it. And I have also like Heisenberg picture to be discussed here, but I don't have any notes. Anyway, I can add those on the fly. So yeah, we have like other theories to represent the quantum mechanics, and one of those is Heisenberg picture. And in Heisenberg picture, the state of the system is considered to be constant in time, and the time evolution being taken up by the dynamical variables, so our observables basically. So I can write something here, something like in Heisenberg picture, the state is constant and dynamic variables are not, something like that. Okay, and yeah, but anyway, those two pictures or two theories are equivalent. So like Heisenberg picture is equivalent to Schrodinger one, Schrodinger's. And to see that, we should consider first like the ordinary Schrodinger picture, take some quantum state psi at time t0, and after some finite time evolution we will obtain psi of capital T state. That's on the page 537 if you have a book somewhere near. So, and that could be described as acting on the wave function using some unitary operator u with capital T index below. So in the Heisenberg picture we just take the same thing, but to represent states there we will take the Schrodinger states and add to those the inverse of that unitary operator. So basically Heisenberg state, Heisenberg states are just something like u minus 1, it's like inverse here, multiplied by Schrodinger state, like psi here, maybe without, something like that. So while doing the unitary evolution by Schrodinger equation, that thing will always stay constant. And yeah, so probably I will leave it as it is. Yeah, and in terms of the observables,
might be helpful to put the bra Heisenberg states as well.
Yeah, but like in the bra case, I think that those will be just
It'd be bra psi and then u. So the u inverse goes with the ket and u goes with the bra.
So if you take bra, it will be something like that, right? And we need, do we need to take the adjoint operator of u minus 1 here?
Yeah, and so this is where we use the fact that it's unitary. The adjoint of u inverse is just u.
Yeah, so it will be just like that.
Mm-hmm.
Yeah, great. So, and for the operators, we will have similar transformations. So, like in Heisenberg picture, our it's about things that I cannot use like smaller indices here, so I will just mark it with small letter here, like h. So like q of h will be just q sandwiched between two u's, and for things to work, we need to do that in this way, something like that. So, and if you now try to act like with like with that q on some wave function psi in Schrodinger setting and in Heisenberg setting, we will kind of have these similar things. Okay, so we can rewrite the Schrodinger equation and obtain Heisenberg equation, and instead of having like the wave functions there, he has the q of h, like the corresponding observable for q trapped in the differential equation, basically. Yeah, and we can show that eigenvalues are preserved in comparison to the Schrodinger picture.
I think you want an umlaut over the O there, so here instead of O in Schrodinger.
But what?
There should be 2 dots over the O in Schrodinger, I think.
Oh,
yes.
It's just hard to type. I don't have that symbol. Yeah, I know, but I just don't have the O umlaut here.
Yeah, I was surprised that you were typing a psi symbol, so
yeah, but I have the motivation to type the wave function right, but I don't have enough motivation for like surnames. Sorry.
It's fine.
Yeah.
Oh, by the way, while I notice insignificant things, it's pronounced linear instead of linear, by the way.
Okay, thank you. So linear, right?
Yeah, a line, but it is still linear.
Linear. Okay, thank you. Anyway, so like at the bottom of the page 537, Penrose basically asks like, what's the profit? Like, do you have any profit of like going to the identical in terms of like equivalence picture? And in some context he says there are technical advantages in the Heisenberg picture, but Heisenberg picture does not help things with regard to the interpretative puzzles of quantum mechanics, and like the problem of quantum jumps hasn't gone away, but now we may have the choice as to whether we put the blame on the state or on the Heisenberg dynamical variables for that jumping. And actually Penrose thinks that jumping matter is simply made more obscure in the Heisenberg picture. So basically no like real profit in it.
I think that there's a bit of a philosophical profit. just because, like, you know, if you come at this from the standpoint of like a classical physicist, then it's really hard to figure out like what the hell is a wave function. But you know, the classical physicist knows how to measure things. He knows what an observable is. And so in the classical picture, we usually talk about like trajectories, right? The position as a function of time. And that happens to be the Heisenberg picture. Is like the position is an observable. And if your observables are the functions of time, that is less confusing to the classical physicist.
And maybe you know, Joe, why does the Heisenberg picture have the matrices in it? Like, why observables are matrices actually? Like, without knowing anything about the quantum states or like wave functions. So, like, the question here is that, as far as I remember, historically, Schrodinger was like theory was put forward after the Heisenbergs, and like Heisenberg came up with the matrix theory on his own, just from kind of observing the physical systems and experiments.
That's a good question. I think that there's actually like a variety of answers to that. I mean, it's not just like one reason why we have. There's not like one experiment. You know, the best answer that I could give, I think, is that a lot of times in more advanced classical mechanics, we find a way to represent the system in terms of these matrices. Like, for example, in rotational dynamics or something like that, you might get a tensor that corresponds to like your kinematic variables, and you might get a tensor that corresponds to your potential variables. So like one example of that, a very concrete example in rotational dynamics is like you might get a tensor for like the moments of inertia, and you might get another tensor for like the masses or like the mass distribution. So that's like a motivation for using matrices in dynamics, but it doesn't say anything necessarily about quantum.
I wonder, because matrix is just a notation, where the point of using matrix is because of this non-commutativity. And so I don't know enough, but I seem to remember that in Heisenberg's their development, what's important with this was the non-commutativity. So matrix, I think, I would guess, would be something to make this non-commutativity easier.
Yeah, but like just by looking on the Heisenberg's equation, we see that if our observable commutes with Hamiltonian, then we will have constant unchanging system.
Oh, that's I could show that by hand if you're interested in seeing that. That's about like this like whether the Heisenberg operator is time dependent, because like basically what you have is the exponent of the Hamiltonian, then your operator, then exponent of minus the Hamiltonian. So if they commute, then you can bring those exponents together and they cancel.
Yeah. Anyway, I think we should finish with the subchapter, and afterwards we can talk just like to finish with the main material. And the last thing I wanted to say on that break, I noticed that scene here, like, you know, the quote from the Heisenberg, I think, that it was about 3 o'clock at night when the final result of the calculation lay before me. At first I was deeply shaken. I was so excited I could not think of sleep, so I left the house and awaited the sunrise on the top of a rock. Sounds really romantic for me, like a dream. Yeah, okay, so back to the original book material. Uh, at least in the Schrodinger picture, we have an evolving state which has a chance of giving us some glimpse of what quantum reality might be like, says Penrose. And the evolution of dynamical variables cannot represent the change in any specific physical system because they do not describe specific systems at all, but rather questions that can be asked of a system, such as what is your position? So Penrose tells us that those observables, they're kind of the questions about the physical systems and not states. So that's why in his point, Schrodinger basically wins or something. And then we have a paragraph about history a bit, that Heisenberg theory was produced first on July 1925, and Schrodinger put forward his proposal half a year later in January 1926, realizing the equivalence between the two schemes shortly afterwards. And Max Born was the first one who recognized the probability interpretation for the squared modulus of the state vector of Schrodinger's wave evolution. It was like summer of 1926, and Schrodinger himself had tried to hold to a more classical field picture of psi. And the general operator framework of quantum mechanics arose out of the work of Heisenberg, Born, and Jordan, and was fully formulated by Dirac and described in detail in his book, The Principles of Quantum Mechanics, first published in 1930. Yeah, and the last paragraph here says that, of course, it may be that when a change is eventually introduced into quantum theory, then there may be good reasons for preferring one formalism over another, and the equivalence between the two may be broken. And this is mildly the case when the quantum field theory arises. And Dirac has made some arguments for preferring the Heisenberg picture in this case. Neither the Heisenberg picture nor the Schrodinger picture is relativistically invariant, however, and sometimes the hybrid interaction picture is preferred in this context. Yeah, so that's it for that subsection. Now we can talk. Any questions?
The interaction picture is a big deal. It ends up being like how you formulate a lot of particle physics sort of stuff. You consider like so just a small explanation on what the interaction picture is like you have a set of states that are constant in time, which you call like the stationary states or the coherent states, and then you have a set of states that interact with each other, and these states are sort of transitions from initial to final state. So you can picture you can think about the interaction picture as like a free and a coupled system. So you basically have two components. One part of it where there's nothing actually acting on the system; it's free to move. It follows all the sort of standard unconstrained quantum evolution. And then in the interaction terms, we have jumps between these states. You can go from one coherent state to another coherent state. So basically the coherent states that have their time evolution is just like oscillating. But the interaction states can switch between each other.
Yeah, so it reminds me about Feynman's diagrams, actually, like particle interactions, right?
That's what it ends up being used for. Like those interaction states that I'm bringing up are what ends up being used in the S matrix, which is like a scattering matrix, and that gives you all the Feynman rules and allows you to draw these diagrams.
Yeah, looking forward for the quantum field theory.
Yeah, I thought, sort of back to this idea of like Schrodinger versus Heisenberg picture. I thought that the Heisenberg picture feels a little bit more natural, seeing as the observables are the things that change in time. But I think you could make the opposite argument and say that, like, well, the way that you measure the observables should not change in time.
Yeah.
An operator in the Heisenberg picture is time dependent, and so like that operator is the way in which you're doing the measurement. So the way in which you do the measurement depends on time in the Heisenberg picture, which it's kind of an interesting way to think about it.
Yeah, so it's kind of like the dualistic nature of the like measurement and the reality. So like observing the reality, right? So we can think that it's stable in some sense, but then to produce like the correct result, we need to vary our observables in time.
And ultimately we get the same results because like what we have on this page here, where you're saying the Heisenberg states are just U inverse psi. If you took that bra psi U and then you did the Heisenberg observable, the U and the U inverse on the left-hand side would cancel out. And then the U and the U inverse on the right-hand side would cancel out. And we'd just get psi, Q, psi.
Yeah. So you're just talking about like sandwiching that scene between those two and seeing that U will go for that U minus 1, and this U will get the U minus 1 from the cat here, and we just will have like the original Q from the Schrodinger picture, and basically that means that sandwiching the QH or Q between those things are like the same in both pictures. So like psi H QH psi H equals to psi Q psi.
Right, and that's, and like we need that to be true because ultimately we measure some value. And so if both pictures are to be coherent with each other, then they have to measure that same value.
What does this U minus U inverse act on Schrodinger's state function mean? Is it like, I don't know, it's like, I mean, what does this unitary inverse do to the, what is this Heisenberg state in relation to Schrodinger state?
It's the initial state in the Schrodinger picture.
Okay, so the Schrodinger state was at time 0, and then you act on the U inverse to transfer it to the Heisenberg state.
I think, the only thing that's not exactly right there is that the Schrodinger state would be at a time t, and U inverse basically brings you from a time t to a time 0.
Yeah. So
that equation on page 537, the phi h was ut minus 1 act on phi rather than phi t.
Yeah. There is no t for psi here because the psi here should be just like fixed one basically. So if you have like psi t in the Schrodinger evolution case, then you will have like psi t, let's write it like that, it will be equal to the u of t over some psi 0, like that, right? And in the case if you have like the Heisenberg state, then instead of just having the psi 0 here, you will have so like to obtain it, like not changing state, so at time t you need to have the same psi 0 basically, in terms of like Heisenberg form here. That means that you will need to compensate for the unitary evolution here, and to compensate you need u minus 1 to be used here, and that compensation will guarantee that your state will be the same in that new picture of like Heisenberg. So, and that psi of 0 in Schrodinger picture in Heisenberg's picture became like a compensating one with u minus 1 in front.
I see. Okay, thank you.
Yeah, and actually it's just kind of reminds me, especially that thing here, that we're kind of passing from one basis in our vector space to another one. So basically we just kind of change one space with wave functions to other space, maybe with matrices inside, and or maybe not sure about this. So because we have like interaction between the like the wave function state and observables here, and they live in different spaces, so probably I need to think more about that. It seems that it just like has some connections. So basically I think that we go from like Heisenberg state space to, from Schrodinger state space to Heisenberg states, and Heisenberg states the states multiplied by u minus 1t here, and they are all of that form, and you can transfer to the Schrodinger state by just multiplying those by ut probably, or ut squared. It's interesting to ask. I don't know.
Yeah, could I share a screen? I think I can write this out.
Yeah, let's try. I will just finish my screen share. One moment. Yeah, you can now.
Okay, I'm just pulling it up. Okay, so you can see my screen now?
For me, the streaming hasn't started.
Oh, interesting. Has it started now?
No, I do not see the live button.
Oh, interesting.
And did you press like screen share button in Discord?
Yeah, and I selected. Okay, is it going now?
Yeah. Now I can see something.
Interesting. It like required me to do it twice. Weird. Okay. So just starting from like what we've done so far, this is the unitary operator that governs time evolution. So if we have an initial state, psi of 0, we can apply the time evolution to psi of 0 to end up with psi of t. And then just, rewriting this equation by multiplying both sides by u inverse, what we end up with is the initial state is just u inverse times the state at a time t. So this is kind of like our starting point. So what we want to show is that psi of t, a psi of t, we want to show that this is equal to psi of 0, a of t, psi of 0. And then just to be very explicit, all right, this is Schrodinger. And then this is Heisenberg. And so I'm actually just gonna expand this out. So psi of t is psi of 0, u inverse. And then so keep the a there. And u, I need hats. Psi of 0. So you see how, I just took psi of t and I wrote it out as u psi of 0. And I did the same thing for the bra. We can plug in these operators and say, okay, well,